So 6-1 is introducing exponential functions. We started off with having our linear and quadratic and absolute value functions that we did at the beginning of class. Linear obviously being a line, quadratic being a U-shape, and then absolute value being a V shape. So the next one in this series of family functions is the exponential function, which is sort of like a line, but it's a curved line, if that makes sense. It's not quite a U, just a curved line. And it's given by the function or by the standard equation of y equals a times b to the x power. Now, please note that the x is attached to the b, not to the a. The b to the x power is merely multiplying, once it is done, with the a. A common problem that I've seen is people want to put that x with the a, or they want to follow the same properties as the a, and that is not what you're supposed to do. So let's talk about the pieces of this function. We have our a, which is the y-intercept. Okay, so this is our a. It is the y-intercept, or follows the ordered pair 0a. And you can sort of see this over in our pictures. We have our y-intercept, which is annotated by the a, and of course it's also on the y-intercept, so there's that too. All right, so then the next piece that we have is the b. The b is what tells us, are we growing or are we decaying? Because exponential functions are really, really helpful in the real world. They help us with banking, they help us with stocks, they help us with bacteria growth or medicine dissolving in the body. They help us with all different types of things. And so a common question is, well, is it growing or is it decaying? And obviously, the more that it grows, the higher it gets. So if b is greater than 1, it's going to be going upward, as we can sort of see here. If it is going to be less than 1, then it's decaying, where it's going downwards. And this also has a ordered pair, which is 1b. And so I went ahead and actually put that on both of our pictures here. So in example 1, and really this follows problems 8 through 18 or 10 through 18 on your homework, but the question for example 1 is, well, determine if this is going to be a growth or decay, all right? And so even if we don't have a picture, we can actually determine this just by looking at our equation, which we already sort of talked about before. We have to look at the b. If b is positive, then it's growing, but if b is or not positive, but b is greater than 1, it's growing. If it's less than 1, it is going to be decay. We are going to add a little bit to this, though, because as much as, this is helpful, what happens if they want us to draw a picture or identify the graph or something like that? So going a step further is going to be helpful for us in the long run. But we can look at letter A. It says 2 to the x power. Remember, our b is associated with the x, so we know that 2 is our b that we're looking for, and it is greater than 1, so we know that it's going to be growth. Now, I, again, can take it a step further. I can say that the y-intercept of this is going to be 0, 1. It's 0a, and there is no a, so think about it like a variable. If you have x, the understood coefficient of that x is 1. Well, the same idea with an exponential function. We have y to the x power. The understood coefficient, if you will, is 1, because the 1 doesn't actually change any of the values. So this is going to be the y-intercept is 0, 1, and so therefore the other point is 1, 2. So it's 1b, but we know what b is, so it's going to be 1, 2. And so this is our final answer. If I wanted to, I could take it a step further and I could draw a quick picture. Now, this is not required on your homework for me, but it is helpful to sort of get an idea of what's happening. You just need to put a point at your 2 points that you just found. So we have 0, 1 and 1, 2. And you just sort of draw your exponential function. You just draw your exponential function as best as you can. So again, it doesn't have to be exact. I am all about sketching. Sketching is my favorite. All right, letter B, same idea. Our B is associated with the x, so that is that 2/3 right there. 2/3 is less than 1, so I know that this is a decay. I can take it a step further by figuring out the y-intercept is going to be 0, 2. I know it's going to be 0, 2 because A is the number in front of B. And then that leaves our final one to be 1b, which in this case is 2/3. So 1/2. So again, if I wanted to draw this picture, the picture of this would look something like this. We got 0, 2, and we got 1 2/3, and that's going to be shorter or less than that 1. So our exponential decay will look like that. Again, not super exact, but that's okay. Now, there is a problem on there that's, I think it's number 20 in your textbook, so I'm going to say 20-ish. I don't really remember what number it is. And what they do is they give you some numbers, okay? And they give you the ordered pair of some they give you the graph, essentially, okay? So they're going to give you something like this, and they'll give you what the actual ordered pairs are. This is 1, 3, this is 0, 1, and then this one down here is -1, and we'll say 1/2 or something. All right, and even though they've given us the picture, we can actually still find our equation very, very simply just by looking at the two pieces that we sort of practiced in part A and part B, and that is looking at the ordered pairs with the 0 and with the 1, 0a, 1b, and taking those and plugging it into the formula, y equals a times b to the x. Well, remember that a is with the 0, so it's 0, whatever the number is, and for this one, it is 1. So I know this is going to be 1 here. The next one is a b, which is associated with the 1, so 1, b, or in this case, it is 3. All right, then I would finally just add that x to the b, and 1 times 3 to the x power is my answer. So all I'm doing is I'm just taking the two most important ordered pairs from the picture, pulling the a and the b from them, and plugging it into the formula. That's all I'm doing for this one. Now, I do want to point out something that in all of these pictures, we have sort of this, our line that we draw every time, it gets really, really close to that x-axis, but it doesn't ever actually touch it. And so something that you need to know about that is that it is called the asymptote. And I think that's how you spell it. I'm not really sure. But the asymptote is a line that the function approaches but never actually touches. So the asymptote will move around depending on what sort of transformation you have, but it is never going to touch. All right, so it's a line that the function approaches but never touches. So in all of these pictures, we get really, really, really close to the x-axis, but we don't actually touch it. So as I said, exponential functions are great for real-world examples. The biggest, most practical example is when you are driving a car. When you buy a car and as soon as you drive it off the lot, the value of that car is going to drop, and it follows an exponential function. So in example 2, it says a car's value follows the function y equals 25 times 0.85 to the x power. And we can pull some information from this. We can look at our sort of our y-intercept, and instead of thinking about it as like a graph, which doesn't really have much, sort of meaning in the real world, instead of thinking about it as the y-intercept, we can think about the a as the initial value. All right, and something about this problem that I didn't write down is that this is in thousands of dollars. So when I look at this car did not cost $25. This car actually cost $25,000, which makes a lot more sense. All right, and so now we can look at B, and we can look at this as sort of our rate or our rate of decay. All right, Now, it doesn't really make sense that our rate of decay is going down by 0.85. That's really high. That's like saying that it decreases in value 85% per year. That's very significant. That doesn't really make sense. And so because of that, what you have to think about is the model, the growth and decay model. So the growth and decay model is the same exact formula as what we had before, but instead of B just being, whatever B is, which is, something that we would have from an Algebra 2 class, we are going to change the B to be 1 plus our rate or 1 minus the rate. So if they ask us, like in part B, to determine its rate, we're actually going to use one of these formulas to figure out what is the rate. So let's start at the beginning. A, determine if it's growth or decay. All right. We know that B is associated with X, so we know that since 0.85 is less than 1, it's going to be decaying. It's going to be decreasing. And that makes sense because in the real world, when you take a car off the lot, the price or the value, it decreases. So we know that to be true just practically. All right, part B, determine its rate. Well, since I know that it is decreasing, I'm going to use the formula A times 1 minus R to the x power. So those are all supposed to have the x power. And I don't even need all the pieces. All I really need is the 1 minus R, because I know that's what B should be. And then the B they gave me was 0.85. So I'm just going to put the two together, and I'm going to solve. So this cancels out. I'm left with negative R equals negative 0.15. I can multiply each side by a negative 1 and get positive 0.15. And if I want to change this into percent, because no car salesman is going to say to me, oh yes, this decreases by 0.15. Nobody says that. They say, oh, it decreases by 15%. So that is going to be our rate. So again, you're just going to take your 1 plus R or 1 minus R, depending on if it's growth or decay, and you're going to set it equal to what B value they gave you, and then solve for R. The final thing is, when will the car value at 8,000? Now, in class, all you had to do is go to your y equals in your calculator, type in the calculator, and then you needed to go to the table. And the table actually shows you all the values. Now, I can't do it on here, but if you have your Texas Instrument, you can do the same sort of thing. And you should see that this is going to be at about 8,000 at about 7 years. All right, and because we haven't learned yet how to calculate sort of when x is in the exponent, and that's okay, we'll get to that eventually. But because we haven't practiced that, we can just go ahead and estimate. So I know it says, when will the value be at 8,000, which is sort of implying it has to be exact, but we're going to estimate for this example. Another problem from your homework is that you might receive a problem like this where it's talking about bacteria. And you are going to follow the sort of same process where it's asking, is this growth or decay, and what is the rate? Well, that's great, except something is different about this problem as opposed to the last problem. In the last problem, we just had t as the exponent, or x as the exponent, or whatever it was. But in this case, we have t divided by 28. And that is a little bit of an issue. So what we're going to do is we're going to deal with that divided by 28 first. So I'm going to ignore the a for a little bit. I'm just going to ignore it for now. And I'm going to rewrite this as 0.5 raised to the power of 1 over 28. All of that to the power of t. Now, I know it's going to be a 1 up here because the understood coefficient of t is 1. Okay, so that's how I know that that's going to be 1 there. And then, of course, divided by 28, that part you just bring over. Now I'm just going to type this part into my calculator, and it should give me 0.9755. And it gives me a little bit more, but I'm just going to round to 4 pieces and then bring back my exponent of t to as the exponent. So now it's very easy to see that this is, in fact, decay. And if I wanted to find the rate, it would be 1 minus r equals 0.9755, and you can solve from there. So I just wanted to make sure you understood what to do for that problem. So the next piece talks about the compound interest. And it follows the formula A equals P times the quantity of 1 plus R over N, all of that to the NT power. And it's the exact same type of exponential function that we had at the very beginning. It's just adding a couple more pieces because this is specifically for money. So as we go into sort of different fields like the science field or into a sort of like a accounting or banking field, your exponential function is basically the same, but they might have a few more specific things to make the jobs of that particular job a little bit easier. Or tasks of that particular job a little bit easier. So for this one, the things you need to know about it is A is still the same thing. It's just represented by P. This is going to be your initial amount. Okay, so it could be like your starting money or your initial investment in a company or something like that. Your R is going to be your rate. So typically when you're talking about bank accounts, they say, oh, well, this gives you a 2.4% interest rate, which is okay, great. But with this one, you have to make sure that you write all of your answers as, or not your answers, but all of your, when you plug it in as decimals. So whatever percentage they give you, just make sure you move your decimal and go from there. All right. And then the next one that you have is that N. This just represents how many times or the number of times per year. So how many times do you compound your interest? Is it quarterly, which would be 4 times a year? Is it monthly, which is 12 times a year? Is it semi-annually, which is 2 times a year? So those types of things you need to sort of take account of. And something you really need to pay attention to is that you actually have 2 ends, not just up in the exponent, but below as well. So you need to make sure you remember both of those. And then finally, our last one is T, which is your time, and it is always represented in years. A common thing that I see people do is they get like information and they say, oh, you can have this in 24 months, and they plug in the 24, but that's the months, not the years. You would have to convert 24 months into 2 years and plug in the 2. So in your textbook, you have an example, which I'm going to go ahead and post for you right now. All right, so in the book it says something maybe slightly different, but it's basically along these lines. It says you invest $9,000 into an account with a 1.26 interest rate. How much would you have in the account after 3 years if compounded quarterly? So there's a lot of pertinent information here. You got your principal, which is the $9,000. You've got your rate, which is 1.26%, and this is the one where you'd have to move the decimal and write it as 0.0126. So I just want to make sure you remember that. How much would you have in the account after 3 years? Okay, so T is going to equal to 3. And then compounded quarterly, that's when N equals 4. Now that I have all my pieces, I can just go ahead and plug it in. I got my 9,000, 1 plus 0.0126 over 4. And I'm going to raise that all to the power of 3 times 4. And then you can just type this whole thing into your calculator and get your answer. So if you plug this whole thing into your calculator correctly, you should get $9,346. And when you're talking about money, you should always round to 2 decimal places. So it should be to 16 cents. And so that is how you use the formula for this. So please make sure you're working on the homework. And if you have any questions, text me on Remind.